Yes.
Okay.
Melanie, that was really loud.
Kevin is a kiss ass.
So we found during our group meeting today that these some of these microphones don't work terribly well. I think sometimes they don't. But hi Isaac, how are you?
I'm good.
So we were talking about you during our group meeting today.
Oh, really?
Yeah. I'm not sure what your plans are for the summer. But if you were thinking about staying in Knoxville, there is a summer undergraduate research program that you could apply for and get extra pay and stuff like that. If you are planning on staying, talk to or send Melanie an email, and Melanie can give you the lowdown. If you're going home, that's fine too. But to give you an incentive, I think there's a pay increase.
Yeah, it's a pay increase. First of all, okay, since I'm not eating the microphone, can you guys hear me?
I can hear you.
Yep.
Okay, so it's a pay increase of like $15 an hour, so from 10 to 15. The deadline's March 1st. You have to write up it's a 2-page proposal, and you talk about like the research you're going to do, the impact, that kind of thing. So if you're interested, I can send you the link. It's also just let me know. If you're interested, email me. I'll send you the link. We can help you get your proposal together, and then you can consider that if you want to, your application to do research with the group over the summer.
Okay.
Right, why'd you laugh?
What's that? No, that's good. If he's going to be here, he's welcome to do research with us over the summer. If he's not going to be here, heck, he can probably do research from Norway.
Yeah.
Right? If you wanted to. Anyway.
Yeah, just email me, Isaac. I've emailed you before, so you have my email.
Yeah, I'll email you.
I think Mary and Ethan got their proposals out in like a few days, so it's not a hard thing to do. A lot of it's just talking about why you want to do the research.
It's only 2 pages. Yeah, I think Ethan put his together last Friday afternoon after class. Second part was a rush.
Hey, but it was still good.
You got it in?
My best work is. Okay. So.
My highest grades were on my last minute essay.
There you go. So just FYI, Kevin, I have a lot of students, most of which have not taken the Thermo-Calc class. I think Melanie sat in on it, right?
Mm-hmm.
I didn't take it, and Sam took it, but I have Serena and Bushra and Melanie, and I have 2 undergraduates, and I have 3 undergraduates because Isaac just started with me and is going to be specifically working on Thermo-Calc and interfacing with TC Python because I can't do it. Actually, he might want to talk to you because I know that you actually have some experience with that.
That occasionally.
Yeah, you do that a lot, and I'm actually very jealous because I've been trying to get Melanie and Sam to do it for almost a year now, but it hasn't happened. So that's why I hired Isaac. Because Isaac's a computer whiz. He's going to do it in like 2 weeks, and then he's going to make me feel like I'm a moron. But that's okay. Anyway, so this course is really to get people in my group exposed to ThermoCalc. And I don't really have a curriculum because I spend my days writing curriculum for phase transformations. But I figured I will at least start by going through some of the basics. And so for those of you that have a laptop with ThermoCalc on it, I think you do. Isaac, did you manage to get ThermoCalc on your computer, or are you?
I have it, but I still haven't.
Okay, that's
started
good.
the
That's
license
good.
thing yet.
So just
Anyway.
a note, I'm leaving at 3, so don't think it's weird if I leave.
All right, so I won't take it personally.
Yeah.
Let me go up here real quick and. Full screen. Okay. So I want to start by showing you the easy ThermoCalc, which is the graphical mode. So I've opened up ThermoCalc here, and when you open up ThermoCalc, this is, and you open it up for the first time, or the last time you were in it, you were in graphical mode. This is what you end up. Yes.
Ethan, do you have ThermoCalc?
Downloading it right now.
You're downloading it? Okay, you can get the free student demo version, which should be enough just for today. And then we can work on getting you, because you can get the full license if you're on campus.
I have a computer downstairs that has ThermoCalc on it. Okay. And when I got here, and Kevin, tell me if I'm wrong, I was told that the ThermoCalc can go on university-owned computers only.
Oh, never mind.
So,
That is my current understanding.
okay. I may have stretched that for a couple of people for a while, because for a long time we could not get ThermoCalc to we couldn't log into my ThermoCalc computer downstairs. But from on campus, you can remote log into the ThermoCalc computer downstairs, and you can use it. I think that's how you folks do it from off campus, isn't it, Kevin?
Yeah, so like I'm logged into the MABE 59 computer right now messing with ThermoCalc.
Okay. So you've logged into the MABE 59 computer itself.
Yeah.
Can more than one person do that at the same time?
No, but technically
No.
there's 3 computers that you can do.
Okay.
You can use the student version in the
Yeah,
meantime.
you can use the student version for now, and then I think all 3 of these folks and Sam have ThermoCalc that they can use on their computers.
Yeah, because I have a university-owned computer.
Yep.
So.
And so you can log in remotely to that, and then we'll figure something else out when Mary's working with it too. Okay. You don't have ThermoCalc yet? Oh man, what's that?
I couldn't find it.
You
Okay.
can, in the meantime, just go to the ThermoCalc website and get this free student demo version.
Yeah, download the free student.
And then you're on a university-owned computer, right, Bushra?
Yes, she is.
So after this, we'll get it on yours.
So I may actually want to chat with you at some point, Kevin, because I have had terrible trouble trying to get my students to be able to connect remotely to my computer. So I have a computer. Let me share my screen instead of ThermoCalc.
Haynes might be a better bet for that.
Haynes is probably a better bet.
We actually have a video tutorial on how to access the MABE 59 computer. I don't know why it wouldn't work for every computer.
Hey.
Will you share that link so that I can figure it out?
Sure. Yeah, I think the problem I'm assuming you're going to have is you're not logged into Pulse Secure.
Yeah, so you can run a VPN.
I have Precipitation.
Okay.
Yes. I think that I need to try it for myself at home, because right now, if you are on campus, you can log into the ThermoCalc computer if you're on campus.
But Bushra, sorry, I'm so sorry.
No, go ahead.
I was just gonna say, Bushra, in the meantime, after this, we'll help you
Yes.
figure out all the various routes.
Yes, and you can easily just put it on your computer as well, because that's a brand new computer I purchased. But technically, through remote desktop here, that you should be able to see.
Yeah, we see.
There's some lag, but anyway, you should be able to go to the thermocalc.mse.utk.edu, and you can either use phasetrans at utk.edu or ThermoCalc user. Ask it to connect. We'll ask you for a password. Password I can give you later, but it's
Password is password.
It is not password.
That's my password.
What's your password? Well, now I know. Now I'm going to come in and I'm going to mess with you.
It has some characters.
How about an @ sign? Is that it?
Wait.
Signs too? And so you can actually log in to the ThermoCalc computer, and you can access ThermoCalc from there. It's a little bit slower than if your computer actually has it, but it's not bad.
Okay, sorry, I totally distracted us. I just wanted to make sure
That's okay.
that everybody had it.
If I will try it from home. I've been meaning to try to do this from home myself through the VPN, but I have not been able to do that yet, or I have not done that yet because I'm never take my computer out at home. Mostly because I have kids and wouldn't get anything done anyway. But anyway, back to the task at hand. We have the ThermoCalc. When you open up ThermoCalc, this is the screen that you'll see if you're in graphical mode. Thank you, Kevin. And you have a bunch of templates, and for the most part, if you're using graphical mode, you're going to be using one of these different templates. And for the purposes here, we'll start out with a phase diagram. So I double click on phase diagram, and it takes a little bit, but it pops up with a periodic table of elements. And then up here at the top, there's a number of databases to choose from.
How do you know which database to choose?
Well, we have a nickel alloy database. Actually, I have 2 nickel alloy databases, 2 aluminum alloy databases, 2 titanium alloy databases, a steel alloy database, a couple of copper alloy databases. I just purchased a high entropy alloys database, particularly because somebody I know is going to start working on high entropy alloys. And plus we have several databases that start with MOB, and those are mobility databases that we'll talk about when we start talking about diffusion. But for now, these databases listed at the top are everything that starts with TC is called ThermoCalc. It's a thermodynamic database for steels, nickel alloys, aluminum, titanium, copper, high entropy alloys. This sub-6 database has thermodynamic descriptions for pure substances like alumina or silica or something like that. So if we wanted to do something looking at aluminum oxide on aluminum, or aluminum oxide on a nickel-based alloy, trying to figure out at what conditions we're going to form some sort of protective aluminum layer, or what oxides a material is going to form if it's exposed to oxygen, we can use that. This sub database to get some information about the pure components.
Is it safe to say that to choose like the most recent version, like deciding between the 2
Yes.
nickel? Okay.
Yes. When I was at NIST, we had TC NI 6, 7, and 8, and there were some differences that were really, really weird. And I know the ThermoCalc people, so I was emailing them and asking them, why the heck are these different? And so there were some things that I wanted to use TC NI 6 for, and some that I would go back and use TC NI 8.
Because all the databases are like compiled from literature, right?
Most of it is literature.
Okay.
Some of it is assessments that have not been published.
Interesting, but ThermoCalc does?
That ThermoCalc actually does.
Okay.
There's one person in particular, Natalie Dupont in France, who's an absolute expert at doing what? What's that look for?
I think I know her.
You may have. She's a short. Is she French? I think she's French. Yeah, she's French, and she actually, I think, makes her living doing thermodynamic assessments. And so she's done. If you open up a database and look at the references, you'll see Natalie Dupin's name all over the place because she's done a lot. She's done a lot of this. But for the most part, if you're working with nickel alloys, pick the latest nickel alloy.
Got it.
We're going to start with TCFE steel because at least for this part, we're going to use steels. If we were doing, say, whoop, I don't want to do that. Come on, cancel. I canceled.
Oh, I get that. I think that's it. You need to choose the database. Wait.
No, it died on me.
Oh no.
One thing I will say as we're getting going here, there are some quirks in ThermoCalc. I think they are working on getting those quirks worked out, but ThermoCalc started in the early 1990s, and they were using one programming language, and as they've built up more and more features, they've used different programming languages, so they've got Fortran 90, they've got C++, they've got all sorts of programming languages that I don't even know what they are. But they're all built on top of each other, and there's lots of loops in there, and so there's lots of quirks in the system. So if you find something that is quirky, you let me know, and eventually if you use ThermoCalc enough, you'll let Paul Mason or Jim Rule or Adam Hope, who are the ThermoCalc folks, know, and they'll say, and they'll report it back to the programmers, and they'll actually work on fixing it for the next
20 years.
Yeah, exactly. They're trying to make it a little bit better. They're trying to update some of the code, but you will find that there are quirks, and sometimes it gets caught up in some crazy things. So what I was going to show you, I'm not going to do it, but you can select other databases. So if we wanted to do a diffusion simulation, or we wanted to do a precipitation simulation, which are things we'll look at later on, you can add a mobility database. So you can have both a thermodynamic database and a mobility database. You know how we talked about atomic mobility and diffusion? That's what's in the mobility databases, or the atomic mobility. And you get that thermodynamic factor from the thermodynamics database. And so it's all coming together now, right?
Mm-hmm.
So for now, we're just going to talk about thermodynamics. We're going to start out with something really, really easy. In the graphical mode, we'll pick the iron, the TCFE9 steels database. And to start, it gives us a periodic table. We'll just click on iron and carbon. And over here, it'll let you define a composition. You don't really need to worry about it because when you go to the next page, you'll define the composition again. Some of the other things that you can do are species. So the elements are considered components.
Okay.
Okay. And what do they have over here as components? Over here as components. These could be different components. They have different ions. Most of what we'll end up doing are just the elements are components.
Where is the C60, C2, C3, 45 under, if you click the iron, yeah.
Those are actually different species of,
It does it for both of them. I think it just gives you all the options under each.
those are different
Yeah, it's the same
species
thing.
of that particular element, of those particular elements that you picked. So if we were looking at, say, an aqueous solution, or an oxide where we could have different oxidation states of iron. We could have Fe+2, we could have Fe+3. We could say, okay, well, we only want to work with Fe+2.
Right.
So, but when we're dealing with just a solid liquid, we don't have to worry about that.
Right, I get the +2, +3, +4, I didn't understand the Cs.
It's just, it's a quirk of Thermo-Calc, right? That
No, it is not. They are actually things I've never used them, but they are different species of carbon. So you have a carbon-carbon double bond. You could have a carbon-carbon double bond in the atmosphere. C60 happens to be a buckyball. Have you heard of a buckyball?
Mm-hmm.
A buckyball is a carbon-based soccer ball on the atomic scale. So these are different, just different species. So C60 is a buckyball. This would be a carbon diatom, a two atom molecule of carbon, a 3-atom molecule of carbon, and so forth. For the most part, don't worry about it. If we start talking about oxidation and or corrosion, then we want to talk about it. I still don't think we're going to use C60. Why it's in there, I don't know. Similar things in under species. You can see we have Fe, the C2. We can unclick all of these things if we don't want to think about them.
Should we?
No, we don't have to, because they're not going to come
Oh,
up.
that's, okay, I understand. Cool.
Under phases, it will list all of the phases that are in the database.
Oh, wow.
So these are all different phases that are in the Steele's database, and there's hundreds of them.
Mm-hmm.
The ones that are not grayed out are systems that are phases that may or may not be important to the particular system that we've chosen. We've chosen iron-carbon, and we know that in iron-carbon system, the only equilibrium phases, at least, are BCC, FCC, liquid, cementite, and technically graphite, right?
Mm-hmm.
So for now, let's make things easy. We'll just click on BCC B2. Now you'll notice here that they have BCC A2 and they have B2 BCC. That's because in this database, they have described the BCC phase and the ordered B2 phase, which is an ordered BCC type phase, as two different phases. If you look at other databases like the nickel database, because ordering between BCC and B2 is always quite important, I think they do this in the HEA database as well, they'll actually be modeled as the same phase.
I noticed that if you click the B2 BCC, the A2 disappears.
Yep.
Mm-hmm.
Yep.
Yeah, I couldn't find it. There we go.
Yep. So we can click on either one. If we click on this one, we've got it. We've got them both covered, right? And it becomes important in iron when you've got, say, aluminum or silicon, because iron, aluminum, iron, and silicon both form a B2 phase. We'll click on cementite, because that's another phase we know is in there. We'll click on FCC.
Which FCC A1?
A1.
FCC1, yeah, okay, so let's see, is there FCC 012 in here?
Well, there's DICTRA.
There's DICTRA FCC and there's FCC1. So the difference is, I don't think there's really any difference in the iron database, but in the nickel database, just like the BCC B2,
Mm-hmm.
the FCC L12, which is the gamma prime phase and nickel-based alloys, are described by the same type of model, ordering model. But DICTRA doesn't handle the ordering. So if you want to do diffusion in the FCC phase in nickel, you may have to choose DICTRA FCC.
Got it.
But we're going to choose FCC. Graphite is also a phase that's possible. Right here, liquid as possible. I think that's all the phases we really need to worry about for the iron carbon phase diagram.
Okay.
So over here, this is after we've clicked phase diagram. So what we're doing right now is we're defining the system. We've defined the elements, we define the components, the species, and we define the phases that we're interested in. The next part is the equilibrium calculator. So this is where you actually calculate, make sure that we're on phase diagram. Okay, so.
Yeah. Oh, cool.
So the next thing on the under equilibrium calculator, we can define different conditions, temperature, pressure, system size, and composition. So pressure, typically we're at 1 times 10 to the 5, which is atmospheric pressure if we're talking about high pressure or low pressure, or something like nitrogen partial pressure in a system containing 17.4, and we want to see how much nitrogen is going to get into that liquid. We could do that. So if we're going to calculate a phase diagram, we need to give an initial condition to calculate the equilibrium, and then ThermoCalc will go out from there and try to calculate all the equilibrium points. Typically, we're talking about a 1 mole system, so everything we talk about is on a molar basis. And
The temperature is 1,000 pounds.
the temperature, it depends on what you're interested in, and we'll see later on. But if we're calculating just a phase diagram, the temperature and the composition that we choose as our initial condition is not entirely important.
Yeah.
Because we just need to define a starting point. If we come in here and we want to do, under my project, say a single point equilibrium here, that's when we would go in and we would specify, I want to know what phases are present at
So you're good.
1,000 degrees Kelvin and a composition of 0.02% carbon.
I wonder if you.
All right, but when we're doing a phase diagram calculation, we just need to give it a condition to start. When we go into the console mode, which is where we're going to spend most of our time, we may have to end up giving it multiple starting points, because sometimes it will miss some of the equilibrium lines. And I think you can do that under advanced mode. But I've actually never done it in the graphical mode to actually specify multiple equilibrium points for it to start calculating the phase diagram. So I couldn't tell you. We'd have to go look it up. But for now, we're going to give it a temperature of 1,000, a composition of 0.01, and notice up here we can specify mass percent, mole percent, mass fraction, or mole fraction.
Nice.
So we've had it in mass percent. So why don't we give it 0.1 mass percent? Calculation type, phase diagram. Down here under this box, we define our axes. We can define mass percent. We could define other things if we wanted to. But calculating a phase diagram, we want composition versus temperature. And we'll start out by calculating from 0 to 100. You can give it a certain step size. I typically use for composition a step size of say 1%. If I'm doing a much smaller axis, like from 0 to 0.1% carbon, I would give it a smaller value. But if I'm doing an entire phase diagram from 0 to 100%, I'd give that step size about 1% to start. Temperature, I typically give a step size of 10 degrees. And my standard calculation is start at 500 degrees Kelvin to 2000 degrees Kelvin, because that's typically about the range where we're going to care. We're going to get low enough, we're going to get up to the melting temperature. If we start doing something like refractories, obviously we may have to go up a bit higher. But for an iron alloy or for a nickel alloy, 500 to 2000. The wider you make those axes, the longer the calculation is going to take. And this temperature here is going to be defined in terms of whatever we've defined the temperature in up here.
Okay.
In previous versions, I've found that if you specify temperature in something other than Kelvin under this calculation diagram, it gives you wonky results. So I always define temperature in Kelvin when I'm doing the equilibrium calculations. Because when we go over to plot renderer, which is the next item down in our tree, we can define our composition and y-axes, and we can actually go over here and we can change that to degrees Celsius.
Okay.
And so number of tie lines, that just changes the number of tie lines it's going to print. This gives us a legend option. We'll just leave it at stable phases. Legend style, we'll just leave it at none because I've actually never used it. We have a composition of carbon from the limits that we specified from 0 to 100. We have a composition, or we have a y-axis of temperature in degrees Celsius. It's linear, but because we're doing it in Celsius, we can actually change this. So we'll actually change it from about 200 degrees Celsius, which is just less than 500 degrees Kelvin, up until, say, 1800 degrees Celsius at a step size of, let's say, 50.
I have a question.
Sure.
You said already that carbon would be 0.1%.
Correct.
If the other two was 100%, 1% carbon?
So what we've done, let's go back to the equilibrium calculator. So this condition definitions. So we've defined one specific point in composition and temperature and pressure space, to be honest, but in composition and temperature space. Pressure we're holding constant at 1 atmosphere. We've identified a point in temperature composition space of 0.1% carbon and 1000 degrees Kelvin. So what ThermoCalc is going to do when it calculates the phase diagram is it's going to start right there. It's going to calculate the equilibrium there. It's going to find that it has BCC plus cementite, or BCC plus austenite. And then it's going to go out from there and calculate other points based on,
That's what temperature you were saying.
what's that?
1 point.
Just like temperature, 1000 degrees Kelvin, 0.1% carbon. That's the initial point it's going to calculate. Under axes definitions, we've defined how far out in composition and temperature space we want ThermoCalc to go when trying to calculate the equilibrium. So we say from 0 to 100, and we said we're going to calculate it by every 1%. So it's going to start at 0.1. The next place it's going to go is it's going to go to 1.1. Calculate the equilibrium there. If it's the same, it keeps going. If you see a difference in the equilibrium phases, then it will backtrack and try to find out where that change in phases comes from. So we could be in single phase BCC. It comes out here 1.1% carbon, and it finds out, oh wait, now we have BCC plus graphite. And so it's going to go back and try to figure out where did that single phase turn into 2 phases. Okay? And so down here under axes definition, we basically set up the grid over which ThermoCalc is going to calculate. Under plot renderer, we're just telling it where to plot. So we're going to calculate from 0 to 100% carbon. We're going to calculate from 500 degrees to 2,000 degrees Kelvin, but we only want to plot it from 473 degrees Kelvin up to 22. Actually, yeah, let's go up to 1600. Up to 1873 Kelvin. So that's all it's going to plot. What these step sizes are, I'm not entirely sure because it's already made those calculations. It's going to interpolate between the points anyway.
Maybe it's dashes on the side?
That's what I would think it is.
It might be, but I don't think so. Let's find out. So we've went through system definer. We've went through equilibrium calculator. We've went through plot renderer. What the tie line is on a phase diagram, binary phase diagram, the tie lines are the horizontal lines within a two-phase region that connect the single-phase regions. And so those are the tie lines. So along that tie line, you have an equilibrium between phase 1 over here with a specific composition and phase 2 over here with another specific composition. And the thing that changes along that tie line is the amount of each of those phases. Okay? Sorry, Ethan, we're going over your head just a little bit on some of these things.
You're good. Keep going.
Are you seeing a phase diagram?
I mean, like basic chemistry
You're
phase.
going to see a phase diagram. It's just that it is the same thing.
Right.
You've seen the water phase diagram as a function of temperature and pressure.
Yes, and not in engineering classes.
Okay, yeah. And so now what we're doing is we've added an element.
Right.
Like we're looking at sugar versus water.
Right.
So we've got sugar and water, and we're holding the pressure constant. So we're basically cutting a line out of that phase diagram that you've seen. And now we've added the new variable composition, and we're plotting composition and temperature and the phases that are present as a function of composition and temperature.
Gotcha.
So now let's click perform. It opens up this nice little handy dandy thing and it gobbles. If you can't read it, this says it gobbled. Don't ask me what gobbled means. Gobbled, gobbled, gobbled.
Oh, no. Oh,
And when you get done,
no. Oh, I'm
it went away.
messing
The gobbled.
All the way?
up. Oh,
What? Hold on, window? Results. And that's what I have to keep opening up and then to see
how I made it.
the bottom part, I had to do window and event log.
Yeah, if you go there and click event log, it actually shows
Why
that.
is
The
this
event log
all-
pops up while it's running the calculation.
Reset windows.
If you click on something else,
We're fine, we're fine.
okay.
I need to do that too.
Oh, you know what? You are absolutely right. What is step size? It's the step size of the axes, and that's way more than we needed. So let's just go down to let's go to 200.
Plot render, step size,
I know, you're so smart.
or.
You are smart, Serena.
You thought that too.
So let's go. Let's perform the plot render again.
I was wondering why we were doing 100%. We don't need to go that far.
We don't, but we're doing this to start.
That's what.
Congratulations, Ethan. You've seen a binary phase diagram.
Doesn't look like water.
No, it does not. But up here, this phase up here
Oh,
is the liquid phase.
Change the configure.
why is mine not labeling liquid?
What's that?
Mine's not labeling what the liquid is.
So what you want to do is to label these regions is go up to a region
Oh.
and right click on it,
Oh.
click add label, and it will, you can custom label, but the default label on a phase diagram will give you the phases.
What you
in
need,
equilibrium.
yeah.
So up here, so these green lines, Bushra and Ethan, these green lines are called tie lines. And so they plot equilibrium lines between over here. Let's right click here. Looks like it's FCC. Oh, I didn't. By default, I don't put the arrows.
All kinds of labels, look at.
Yeah.
Oh,
So by default, so over here, whoa, where'd it go? Where'd it go? Where'd it go?
How do I get rid of it? Delete.
Yeah, you have to delete.
Yeah, Bushra and Ethan, the section in Callister where they introduce phase diagrams is really well written. So I always suggest reading that before next week, just to get a better idea of like some of the stuff we're doing.
Will you put your Callister PDF on the drive, on the group drive? So
Yeah, I can do that.
you got, because you had access to it, the group drive, right?
Yes.
Barry, yeah,
Yeah.
Barry just emailed me the most recent PDF.
Oh, you did?
Yeah,
Okay, awesome.
So, but Bushra, Callister, yeah,
Yeah,
okay.
you have Callister. So these tie lines, they represent lines of equilibrium between two different phases. And over here, if we were to look really, really close, we'd actually see something similar to what we see over here. This region right here that I've labeled FCC, this is the single phase FCC austenite region. So FCC austenite is stable up to a composition of about
Did you, to change the x-axis, did you change this, or is there something
about 2%.
to get, I don't want the full 100.
Way over here, because
I didn't.
iron does not substitute very well
You did.
for carbon in graphite. The solubility, the amount of iron that you can put in graphite is like 0. And so that's why you see this go straight over to 100%. This orange line, yeah, Bushra.
I have the question. I know what highlights are. but
Okay.
Why did you give one?
What's that?
Why did you define highlights of one?
I left it the way it was. To be honest, I almost never do put tie lines on. And so
Hey,
But you don't have to.
you don't have to put if you put tie lines equals 0, you get a much cleaner phase diagram.
tie lines.
I don't like tie lines either. And when you go to a higher, order system, when you go to a ternary system or a quaternary system, and you plot something, composition is a function of temperature, the tie lines don't necessarily have to be straight, horizontal. They don't have to be in that plane, because now you're really looking at a slice through a 3-dimensional phase diagram. And so those things could go anywhere, so they really don't mean a lot in a ternary phase. Unless you plot it composition versus composition as at a specific temperature, which we'll do when we get to a ternary phase diagram.
Have you looked at ternaries yet?
Yeah.
I love ternaries.
Ternaries are fun.
They're so much fun.
Yep.
Yeah.
Yep. And so this is what we got. Now, because we're looking at the iron-carbon phase diagram, and beyond about 10 mass percent carbon, all we see is something plus graphite. We don't have to plot everything all the way out to here.
We already did it.
You guys are so far ahead of me. So we go back to
Yeah.
our plot renderer. We can switch our automatic settings, and we can just go out to, say, 10%. Let's make it a step size of 1.
Ah,
Is that what you did?
really good Mary.
Plot it again. Oh, go away.
It just adds the little tick marks.
And so now we're not plotting all the way out to 100%. Now we're plotting out just to 10%. And we can see everything over here where we're, most interested in a little bit better. We were talking about delta ferrite before. We zoom in up here. I think I got to right click and do it. Arg. So I zoomed in on this little plot. So up here, this is the liquid again.
You did that by right clicking?
Yeah, if you right click, and I think you can only do it from top left to bottom right. If you right click and hold, you can zoom into specific areas. Zooming out, I think you have to reprint the diagram. Yeah, it's not exactly the best, but to show you guys what.
Cool.
So over here, this little region right here that I put this in, this is the delta ferrite region. So we talked about earlier in group meeting that pure iron goes from liquid to BCC, and then down here, this big region right here is FCC. Then when you go down further, you get back to BCC. But
And so, whenever, so you have liquid up there, and then you have, well, it's harder to see now, but we can do it in another area. You have like liquid, and then an area, and then on the other side is FCC. So that region in between the two liquid and FCC is liquid plus FCC.
yeah, so this guy, that's what happens when I push the. Let's just add another label. It's because my fingers are fat and I'm pushing. I'm right clicking and right. Yeah.
I have like 8-inch long nails. I have to be very deliberate.
So what Melanie is saying on a phase diagram is that right here, this region right here, this diamond region that I've got FCC in, this is single phase FCC. This region up here that I've got labeled twice is a liquid. And for a binary phase diagram, if we have a single phase region and a single phase region, the region in between is a mixture of the two phases on either side.
And we have like it very right now, but all those lines that separate those phases all have like special equations and that relate to like Gibbs free energy and stuff like that. So it's actually pretty easy to calculate a phase diagram.
Yep.
Gotcha.
Yep. Yeah. And in the iron phase diagram, they have even cooler names: A1, A3, A something something. I can't remember what all they are. I don't remember what they are. You'll probably at least see them in Callister when you take 201. I don't remember them.
Oh yeah, you're gonna see a lot this particular.
Yes, actually, this is not the phase diagram you're going to see a lot. What?
The iron carbon phase diagram?
You're not going to see the equilibrium iron carbon phase diagram, because graphite is the equilibrium phase.
Oh.
What do we normally talk about when we talk about the iron carbon phase diagram? We talk about cementite. So if we want to calculate the iron Fe3 cementite phase diagram, we come back up here to system definer. We can unclick graphite. We can go back here, and I think you can probably, under advanced options somewhere, I don't know where, I don't know how to do it exactly in the graphical mode, but when we unclick, it's not going to consider graphite anymore. So when we recalculate the phase diagram, it will go through and it'll gobble everything up.
That totally changed stuff.
What's that?
When I unclicked cementite.
Did it?
Yeah, mine changed.
Did it change? It changes some, yeah. Oh, look at that.
Oh, what is that called? There's a special name for that.
For what? This?
Yeah, how it goes down like that.
Oh,
This?
that's okay, so that, when it's a straight line, it is
Special kind of intermetallic.
Yeah.
When it's a straight line, so this right here, this line right here represents cementite, which is a specific phase with the composition Fe 3 atoms for every carbon 1 atom.
That's got
And when your single phase is a straight line, it's called a line compound.
That's it. Congruent melting.
That is exactly right. And so when this line compound comes straight up to the liquid at this specific composition, which is at 6.7% weight percent carbon, which happens to be, without having to do the math, Ethan, what do you think 6.7 mass weight percent carbon is in atomic percent? If we have 3 iron atoms for every carbon atom, the carbon content has to be 25%. 25, 75, 3 to 1, right?
Yes.
Okay, sure. So, that's it. I was trying to give you all something easy. I gave you Fe3C, so you know what the atomic ratios are.
Yeah.
So, okay, it is 3:30 on Friday. But you are absolutely right. Good job, Serena. Good job, Melanie. This is called a congruent melting material. So when a non-single component system, non-single component phase, like cementite, comes up to a single point and melts, that's called congruent melting. So if you had a liquid with the composition 25 atomic percent carbon or 6.7% weight percent carbon, and you cooled that down under equilibrium conditions, it would congruently melt at a single temperature, which is roughly equal to somewhere around 1200 degrees.
I think it's like 1273.
If instead you had something that was about 6% carbon right here, and you cooled it down from the liquid phase, you would initially come down here into this 2-phase region here, and it has liquid on one side and cementite on the other side. So in this little region that looks like almost like a triangle with a curved hypotenuse, that's liquid plus cementite. So you form cementite first, and in this triangular area here, you have 2 phases, liquid and cementite. And as you go down farther and farther and farther, you get more and more cementite through something called a tie line. You can calculate that. I'm not going to go through it today. But once you hit this red line right here is called the eutectic temperature. And below that, all of the liquid that's left that hasn't been already transformed into cementite will transform into FCC plus cementite. So when you drop down below this red line, you end up with no more liquid. You end up with FCC plus cementite, 2 phases.
When I did phase diagrams, the only thing I could remember was
You see that?
melting.
So
Peritectic, eutectoid, anything out of the.
it gets hard. I mean,
I get like the labeling makes sense.
yeah, the labeling makes sense.
Everything else, no.
Solid.
Now, I will say
Like, ick.
The amount of times I've heard
a little bit of
Eli and Connor,
to
it doesn't
give
matter. I will never learn.
you a heads up on 201.
Yeah.
These line compounds here can start to confuse people, because these line compounds are really the single phase regions, right? So this is cementite plus FCC. The single phase region of cementite is actually breaks down or compacts down into this single line. So on the other side of this line compound, we have another two-phase region. So it's not exactly like up here where we have two-phase region with a single-phase region next to it, because the single-phase region is actually collapsed. So that tricks some people up, particularly some people that are non-material science majors.
And some of us
that are. Because, you know, when you teach it, you're teaching single-phase region, two-phase region in the middle. So you're looking for a single-phase region right next to a two-phase region. But when you have one of these line compounds, the single-phase region compresses down into a line, and so it looks like you have two-phase regions next to one another. So that's how you calculate a phase diagram using the graphical mode. What's that? Where?
Oh, so after we removed the cementite, I expanded it out because I was like, well, it keeps going down, and then it says that that's a liquid and cementite region. So then I expanded it out to look at it, and then if you do it up to 50 is where the second liquid region starts, but it's just.
This is probably a good time to point out I didn't.
Because I was like, dang, that's a low temperature to have. I didn't carbon. Does carbon even melt? Or does it just evaporate?
So this is liquid 1 plus liquid 2 region right here.
Right, so where's the solid carbon? Do we need to zoom?
We are ignoring pure graphite.
Okay, that's why.
And this is, and when you start looking at regions that are way outside of where normal people would look at, or when you start suspending the equilibrium phases, this brings up a good point to consider in ThermoCalc. The way the databases are constructed, sometimes you can have false miscibility gaps, or you can have miscibility gaps over here, because in reality, nobody's ever going to look at iron carbon at 700 degrees Kelvin way out here at 80% carbon, right? So there is no experimental data.
Okay.
So there is no experimental data way out there. So the way they make these thermodynamic assessments is they have free energy functions, and they take the experimental data and they optimize the terms of these free energy functions to match the experimental data.
It's like Kesher's project, but on crack.
Yeah.
Yeah. So where there is no data, or where you're not considering equilibrium, like way out here at uber low temperatures and high carbon contents without graphite, you can see quirky little things like that. That's not a quirk in ThermoCalc. That's a result of the definition of the free energy functions and the way that they were optimized. You can also sometimes see, and maybe even in this system, that at really high temperatures, way up here, say above 3,000 at 3,500 to 4,000 degrees, you can see an inverse miscibility gap, where we've got a single-phase liquid, and then you have this big old semicircle up here where this single-phase liquid is supposed to separate into two different liquids.
You can keep your inverse miscibility gap. I don't want that.
That liquid plus liquid number 2 would never happen.
No, it would never happen. That is an error associated with the way that the thermodynamics have been defined and optimized.
Okay.
And you can have similar things that happen way up here. A good thermodynamic assessor will take into account as much of that as they possibly can. Now, 750 degrees at 80% carbon without graphite present, they're probably not going to take that into consideration, which is why, if you look here, there's this thing that says, hey, we're going to have two liquids way out here. In reality, it's not. The thermodynamics way out here are so far away from equilibrium that whatever you calculate is junk anyway. Okay? So there are some quirks that can happen in there as well. Let's see.
Does it melt or does it just sublime?
Good question.
The Wikipedia does not have a melting temperature. It just has
Yeah, it may just sublime.
Sublime with room?
Atmospheric. What's that?
Sublime with room? Sorry, it was a really dumb joke. I'm so sorry.
You got the Walmart rollback on that one.
Anyway, yeah, I get you.
I'm so sorry, we were talking about good research questions. Talking about
Okay, I've lost my train of
2003
thought.
music.
Does anybody have any questions on how to calculate a phase diagram in graphical mode?
I feel good.
Okay, I think we're going to spend. Does anybody have to go anywhere? We can stop right there and go and wait till next week, or we can go through calculating the same phase diagram in console mode this week, or we can wait till next week. Anybody have any preference?
Why did everybody look at me?
Nobody has any preference. I'm gonna go ahead and look at.
I have an idea about
I have an idea as well.
it.
So,
I've done it like 3 times, but it's been a while. You define the moles, you define the temperature. Let's just do it. Let's do it.
we are going to console mode now. So up here, I think people like Isaac will probably feel more comfortable in console mode.
I like buttons. There ain't no buttons anymore.
This is one place where I feel more comfortable in console mode because I actually learned on a version of ThermoCalc where there was no graphical mode. So in console mode, this is what pops up. You start out at the system level, and anytime you get lost, you can just type in question mark, enter, and it will give you a list of the possible commands.
That's not all the commands though, right?
That's all the commands that you have access to under the system. Every time you change to a different thing, a different module, you will get a new set of commands. So we type about, it tells us about the ThermoCalc software. If we type in info or information, it will give us a list of things to tell us information about.
When I type in info, it just says which subject or purpose.
Yep. You type in info, and
I don't even get the.
if you type in question, if it asks which subject, you type in question mark, it gives you a whole list of subjects.
How do you clear it?
How do you clear it? Just hit enter.
And then, no, mine still says which subject.
Hit enter again.
Oh, okay. Can you clear your console?
You clear your console, it just keeps running. Actually, if you type in exit, it'll exit the whole thing and it'll go back to system again. Note, however, that when you press exit, anything that you have done is wiped out.
It's like that, yeah.
There's no like CLC.
What's that?
There's no like CLC, like clear windows.
No.
Go binary.
What's that?
Go binary?
Go binary, come on. Okay, we can do that one first. But the first thing that I want to show everybody how to do is to set log file. Okay? So set log.
And you have to do the dashes.
Yeah. What's that?
I don't think it matters if it's dash or underscore.
It doesn't matter if it's underscores. I use that. I use dashes because it's one less having to hit the shift key. And you can actually just abbreviate everything. As long as the abbreviation that you put in is not
A different command.
it doesn't have more than one meaning. So I could say set log, S-L. It'll know to set a log file.
Oh, I remember seeing that in the Thermo-Calc class.
Yep.
And okay.
So S-L is set log, and it will pop, a box will pop up, and you can name your log file, anything. Let me go to, I don't even know what to put this under. We'll just call it log for now. And it'll ask for a heading, so you can put a heading in there. Most people don't. Yeah. So now, from now on, I've set this log file, so from now on, every command I type in, it will record. And it records it under the file name you gave it, which has a .tcm. So my file is log.tcm, and TCM stands for Thermo-Calc macro file. And so you'll also notice that under system, you have macro file open. So what you can do is you can set your log and create a macro file of all of the commands that you put in to do a specific problem. For instance, calculate the phase diagram. So that the next time you come into ThermoCalc and you want to do the exact same thing, instead of having to type in all of those commands, you simply say,
Open macro.
Macro file open that, and it will automatically run through all of those commands for you. So the one place where these abbreviations like S-L won't work is if there are multiple things that it could be, like say, set plot environment or set poly. If I say set E, it says ambiguous.
Mm.
So set E. E is set plot environment.
Okay.
Okay.
So when we log into this, I'm horrible at setting a log file. And as a result, I am really fast at doing things to calculate a phase diagram. Because I've done it an ungodly number of times. My fingers know S-A-B, space 1, W, parenthesis, open parenthesis, C, close parenthesis, 0, dot, dot, or 0 space 0.1, space 0.001. That's set axis variable 1, weight percent carbon from 0.1. I know, I mean, it just does it. I strongly suggest that you use set log because it makes things a lot easier. It saves you a lot of time, and I'm horrible at it. And I probably could have been a lot farther along in my life had I not spent all my time typing in set axis variable 1, weight percent carbon 0.1. So we set the log file. If we're going to calculate a phase diagram, because Serena brought it up, we will start by cheating. Thing that so if we want to do something, these are all the high-level commands where we can set options and open files and open macro files. And apparently it's got an HP calculator in it that I've never used. The first thing that you're going to do is you're going to go to module. So GM. And it'll say module name. We'll press question mark to see what the options are. So it's got a whole bunch of different options here. I wasn't going to show you binary diagram easy, because notice there's easy on the end of it, because it is fairly straightforward and fairly easy. But we'll do, what are you laughing at, folks? Laughing at me?
I'm laughing.
Okay, so, I'm just, all right. So we'll start by calculating the iron-carbon phase diagram the easy way. Module name, I'll type in bin, because bin is the only thing, but the whole command is binary diagram easy. It might.
Oh, yeah.
Does it? And it will come up thermodynamic database module, current database, simple binary phase diagram calculation module.
So does it automatically go into the steels iron?
Yes.
Mine automatically went to TC bin.
Binary, there's a binary database.
Yeah, so with what, did you just go to TC?
Oh, no, ours is the same. Mine just says, yours says it too. Current database, steel/iron alloys V9.0. It's the third line.
Yeah, I see that. But when you go into, so the first thing it does, I guess, is it's going into the database module to retrieve the database. But when you're doing the binary diagram easy module, the default turns to bin. Is yours down here? Data?
So that's what it was.
That's what it is by default.
Okay.
So when we go to database, when you go D, the default is the steel database.
Okay.
But if you go bin, it changes that default database to TC bin when you go into it.
Got it.
So if we do the question mark, it'll give us a list of all of the databases, just like we saw in the graphical mode. Let's use TCFE9.
Mine says cannot use.
We cannot use this database. Well, maybe that's why I didn't want to do it. So let's use go bin, and I use FE demo. So this is why we don't use TC bin, or we don't use go bin. Go bin, we'll use TC bin. You'll ask us, what's our first element?
Iron.
Fe for iron. What's our second element?
Carbon.
Carbon. What do we want to do? Do we want to calculate a phase diagram, a phase fraction, or A curve, which is the free energy curves? Let's calculate phase diagram, which is the default.
So what do you type for that?
So I just hit enter because it's typed for phase
Got it.
diagram.
Whoa!
Whoa, boom,
Bam.
bam.
That is beautiful.
And what's it do? It calculates the phase diagram for us.
I'd argue that was easier than the other way.
Then
Graphical mode.
it is.
You
What?
get to
What's
see
wrong with
your
it?
axes, it has the tie lines.
It's got the tie lines. It goes to a mole fraction of 0 to 1. Got the stupid tie lines. And what I really hate is the fact that it's got graphite.
Yeah.
Now, post is the plotting module in the console mode. So let's go over here. Let's click question mark. We have a whole new list of commands. So we can, let's set the diagram axis, because we don't want to plot mole fraction, because nobody talks about iron-carbon diagrams or iron-carbon alloys in terms of mole fraction or even mole percent carbon. We always talk about weight fraction or weight percent. So let's set diagram axis. It will ask us which axis.
X.
Let's try the X. What variable do we want to use?
Weight percent carbon.
So weight percent, we could type in weight dash percent or
WT.
WP.
P.
We could use weight fraction. W dash F.
Okay.
One thing that you have to think about, and I've done it a lot, is M-P is not mass percent, but it's mole percent.
Hmm.
M-F is mole fraction. So if you want weight percent, you have to think weight percent and not mass percent. It's especially difficult for me because at NIST, weight was not something we thought about. It was always mass.
Interesting.
We never talked about atomic percent either because that was forbidden. You can't have a fraction of an atom unless you're a nuclear physicist and you break atoms apart. So we talked about mole percent. And even then they didn't like it. It was mole fraction times 100. But anyway, I further digress. Let's change set diagram axis. X, WP, for what component?
Carbon.
C, booyah. PL is short for plot. Booyah, our new phase diagram in mass percent. Sweet. So, why are we going out to 100%? We don't need to go out to 100%. Let's take a look at our options. We can set scaling status, which will let us set the range over which we want to plot each axis. So set scaling status, which axis? X. Automatic scaling scaling? No, because that gives us 0 to 100%. Boom. Min value? 0. Max value?
6.67.
Let's go up to 7, just so we can see where that is. Although, it's not in here yet, but we'll go up to 7. Boom. Plot. Booyah. Why are we plotting it all the way up to 2,500 degrees and all the way down to 0 degrees Celsius? I will tell you that ThermoCalc is based on primarily experimental data for phase equilibria between solid phases. We typically are not going to have experimental data down at 0 Celsius. So ThermoCalc, and plus the way that the free energy functions are defined, anything below about right around 0 Celsius is going to get fairly inaccurate. I will tend to use the free energies of the primary phases like BCC, FCC, HCP, maybe liquid, but not so much liquid, but the primary solid phases down to about -100 C. So if I want to calculate, and we'll get to this some other time, the Martensite start temperature for a material. What I need to do is I need to calculate the free energy of the BCC and the FCC phase down, when we've got nitrogen, way down to 200 degrees C or lower, or 200 or 100 degrees below 0, so -100. So I will tend to use it down to maybe 273. Anything below 200 K, and the way the functions are defined, you have a natural log term. What is the natural log? What's the natural log of 0? Undefined. You have a 1 over T term. What's 1 over T? Goes to infinity, right? Or it goes to 1 over T goes to infinity. So when you get down close to 0 degrees Kelvin, all those free energy functions that they use to describe the free energies of the phases, they go to heck anyway. So I tend to use the free energy functions down to about 200 K. But free energy functions for intermetallic phases, I stay away from. I will only think about BCC, FCC, maybe HCP down to 200 K. And that's if I want to calculate things like driving force for Martensite formation.
And who would want to do that?
Who would want to do that? We don't care about Martensite,
No.
right?
Why aren't there any tie lines in the austenite?
It's single phase. It's a tie line between what and what?
Okay, just.
A tie line is in a 2-phase region.
Right.
So we could also go in here. I hate tie lines. Set
STS.
STS. Whoop.
Ambiguous. 0.
Plot.
And then it says error, but then it plots it.
Booyah. Does it say error? It didn't say error to me.
It told me error.
Oh, it did say me. So why are we plotting?
Oh, I said no.
I said no.
But it still gave me no tie lines, so
Set scaling status.
we get what you mean.
Y.
Just no.
Go. Minimum value, let's go 500. Maximum value, let's go 1600. Wow. Booyah. Problem is, we still got this graphite in here. Now, there is something under here. Suspend phase in plot.
Why isn't it showing up in our legend?
Because we don't see the single phase graphite region.
So our legend is only going to show.
Our legend only shows single phase regions or it only shows those regions that we've.
Because that's not what it did in graphical mode. But
No, it's not. We can set label something else. I can't remember if this is F or E. Set label F. Okay, set label E.
Oh.
Blickety bloppity blue.
When you did set label E, that like.
That gives
legend
us.
for everything.
Let's see. This gives us the equilibrium phases along each of these lines. So, along the black line, which we have labeled 1, the phases in equilibrium along that line are BCC on the left and graphite on the right.
But the E, is that everything or equilibrium?
Oh, yeah, sorry. Set label, question mark, and it tells you what it is. And to be completely honest, let's see, what is F? As D with changing colors. D, as C, but with curves with same quantities have same number. C, list axis quantities. What exactly that means, I'm not entirely sure. E, as B with changing colors. B, as A, but curves with same fixed phase have same number. A, list stable phases along line. So that's what this guy is doing.
Okay.
It's listing the stable phases along that line.
You did E.
What's that?
You did E though.
Yes.
E.
But what is E? E is as B, but with the colors changing. B is as A, with the same fixed phase, at the same number, and you have to go back to A, and you find out that E is list stable phases along the line, but with the fixed phase, have the same number, and with changing color.
If you follow the trail.
Yeah.
If
So,
you follow words, A.
honestly, when we're calculating a Scheil curve, I like to use the legend, but in some, depending on what you're plotting, the legend gives you gibberish in Scheil, because the legend is really designed just for the phase diagram, so it turns out to be some crazy stuff. You can't figure out what it is. I think when we plot a Scheil, one of them gives you X comma N, and it'll have 1 X comma N, 2 X comma N, 3 X comma N, and that's all it says. And so, I don't know what the hell it is. So when I would really want to use the legend, which is when I'm plotting, say, phase fraction is a function of percent solidified, the legend doesn't work very well. So a lot of times I will want to I'll have to go back and figure out which line is which, and I'll just label those curves.
Okay.
In the phase diagram mode, where it actually works halfway decent sometimes, I'll never use it because I end up adding a label in each one of the phase fields.
Right, okay.
So it's useful when you're trying to figure out what's where, but it's not always the most useful thing when you're calculating phase. There are some other things that you can do when you're plotting different, say, experimental data on top of a phase diagram, that it does come in handy, but I've never plotted experimental data on top of a phase diagram because I've stayed away from thermodynamic assessment, which is where you would want to do that, and plot the experimental or the experimental data on top of your, calculated phase boundaries to show how good you did it. I've stayed away from that like a plague because it's a pain in the rear end. But
Is that where you would really incorporate TC Python so you could get it to do, you could get Thermo-Calc to do this, and then you could use more of just Python to insert your data points overlaying on that?
That you can do in Thermo-Calc, and people have been doing it in Thermo-Calc for a long time.
Inserting your own data.
Inserting your own data.
Okay.
If you go under here, you can append experimental data.
Okay.
And so you can add that. And we can do that at some point in the future. It gets harder, and I think this is some place where if you know Python, you can do things a lot easier in Python, because as you can see, some of the commands in here can get a little weird. As B, but with changing colors. As A, but with numbers being the same. So if you know how to do that in Python, and hopefully about 3 or 4 months from now, maybe less, Isaac will be able to say, hey, yeah, that's easy. Here's how you do it. And he just writes a little script and we go blah, 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 and it's done. Right, Isaac?
Totally.
Sure. I saw that you tried to talk, but I didn't hear you.
Oh, I said totally.
Totally.
Love it.
Okay. Let's see. It is currently 4:06. Okay. We calculated the phase diagram. Okay, so I did want to show you suspend phase and plot. So suspend phase in plot. What phase? We'll try graphite.
And you just type in, okay.
Plot. Well, that sucks. It just pulls out all the lines where graphite is. Where I really don't understand it. I don't know what use it is. I mean, maybe
It doesn't exist?
it's exactly what it does. The phase doesn't exist, so none of the lines that involve it exist anymore. It's one of the dumbest things I've ever seen. I've never used it. I've tried to use it a lot, but I've never used it in practice.
Isn't that like a set phase?
What's that?
I thought there was a set phase, or maybe that's when we're not in Go binary.
Okay, so let's try some back. Means go back. And because we're in binary diagram easy, it goes back to system.
Okay.
So we can't actually, I was hoping that we could, choose the phases in binary diagram easy, like we could in graphical mode, but you can't.
Okay.
So the last thing I want to do today is to do a binary phase diagram the normal way. Why is?
Go data.
So I'm going to exit first to get back to just normal. Exactly. So
See, I have been doing stuff on my.
I exited, so now I'm going to reset my log file. I'll make this log 2. And Yes, the appropriate command is go module and then database. So if you go M, D, whoops,
Wait, go,
go M,
I thought you could just go straight.
you can.
Okay.
then what does go M show you?
Go M goes to go module, and then you pick the module.
Okay, and we
And
want,
from module, you can click DA for database. Oh yeah, it doesn't,
If you go straight to go data, it takes you to the TCFE9.
yes. Okay, so that's what I was going to show.
Okay.
Go sys. So we're back to system. So in terms of the modules, under the system level, it will recognize these modules. So you don't have to go to module and then select data, database, or binary diagram easy. You can go simply straight, go data. And it takes you straight to the database module. Okay? Under database module, we have all of these things, and a lot of them will look similar to what we saw under graphical, although they're words rather than boxes. So we can define the system, we can define elements, we can define species, and so Suresh says define system. I always define my elements.
You do them at the same time?
Define elements, and you can go
You do FE comma C or just space?
FE space C. You can also type things on a single line. So instead of DE enter FE comma C, you can go DE or D-E FE space C. And that's the same thing.
Cheaper.
And I believe that if you put a comma in, that is equivalent to an enter. But I don't know for sure because I've never gotten that, because I've always, I've never compounded my entries that much.
Okay.
I think it's comma,
Okay.
but I'm not sure. It will become important if you start doing your log files, because it will shorten things. And when we go to poly 3, it would help if you did that. So, okay, so we defined our Fe and carbon. We're just going to keep all of the phases in it. So right now, it's the default phases that are iron and carbon are involved in. So it's the same phases that we had automatically listed in the graphical mode. So we're going to type in get for get data. And here are all the listed references. I don't see Natalie Dupin. And this one, Bent Hallstedt, he's a big guy. Lou's a big guy. Dinsdale has about, what's that? What?
Dinsdale.
Alan Dinsdale.
That's a good name.
Yeah. All right. So it has now collected all of our data. So we want to go to module, and the poly 3 is our actual calculation module that we're going to calculate phase diagrams. So we want to go P3. So it's in P3 that we've actually moved from the defined system into the equilibrium calculator box when we were in graphical mode.
Mm-hmm.
So now we have our data, we want to set our equilibrium condition, and we want to set our axes. So when we set our axes, it'll actually pick a value along that axis. So first thing we'll do is we'll set our axes variables. What's that?
S-A-B.
Exactly. S-A-B. 1, W open parentheses, C, close parentheses, 01.01.
I do not have S, it's saying S-A-V is not a command.
Are you under poly?
Yeah.
Says no. It should say poly right there.
So you need
Module.
to go P3.
I said go P3 and then it's still making me sense.
What's your command prompt?
Go
Write
P3.
poly instead of P3. Right, actually write go poly.
Booyah.
It wasn't working for some reason.
Okay.
And then now do the
S
and B.
dash A dash B. And then,
One for axis variable 1.
okay.
And I put in WC from 0 to 1, my 0.001. So when you're in the console mode, you don't have the option of using weight percentage or mole percentage. You have to use fractions when you're setting up your calculations. So,
But then you can just set your axis later.
but when you go to plot it, you can then set your axis. You just have to define everything in terms of fractions.
You have to have spaces in between all those, correct?
Correct. Enter. It says the command in full is set axis variable. Condition WC equals 0.1234 created. So it automatically creates a thing 12.34% along that axis variable. Why it's 12.34? I don't know. Probably because whoever wrote the code said, hey, that's a cool number. It happens to be my favorite time of the day. It is.
Well, I can't see.
So the next thing we want to do, set axis variable to,
Oh, I can't see that either.
so for the second axis variable, we want to set that as T. And we don't have the option, at least that I know of, to use anything but Kelvin when we're setting up the problem in poly. But we can then always change the axis variable when we plot it. So when you're setting the second the temperature axis, it's in Kelvin when you're in console mode. And my default is 500 to 2000. My default spacing is 10 degrees. So set axis variable, axis number 2, the variable is temperature, T, from the low limit is 500, the high limit is 2000, 10. So we could do that just by set axis variable, to condition, T, low temperature, min value 500, max value 2000, increment 10.
Any issues?
So now, let's list conditions, LC, enter.
Freedom 0.
Mine says, oh yeah, you're using the 2020 version. For some reason, the 2020 version does not automatically set T, or set N equals 1 and P equals 1 times 10 to the 5.
So just type N equals 1.
Because of all that NASA
So
stuff.
now you can say set condition, S-C,
You're using the same version as me.
Mm-hmm.
N equals 1, space, P equals 1E5.
Which was already set.
Cool.
Because I think,
The new
Melanie, you
version.
have the 2021A
I
version?
have 2019A.
Okay, so it should have automatically set yours. Okay, and so eventually I did put up the new Thermo-Calc, so you can actually upgrade your version to the 2021A. Not like there's going to be much difference.
Yeah.
But in 2021A, it does not automatically define those, but it does recognize that you've defined everything but N and P. So if you don't define N and P and you click the next thing, which is compute equilibrium, it will automatically define those terms.
Okay.
So the next thing is compute equilibrium, and it will compute that first equilibrium point that we're going to start at, right? So if we list equilibrium, L-E, output to screen or file, to the screen, the options, there are a lot of different options. There are 4 different options that we can switch. We'll just type the default.
What is the default? I mean, you hit enter and it does the default. What is it? VWC.
What's that? Yeah, the default is VWCS. So let's go list equilibrium to the screen by default. So V means fraction order, value order or alphabetical order. So when it lists the equilibrium phases, it's either going to list it by the amount or alphabetical. Typically, I say list them by the amount. The most first, the least the smallest.
Mine's different than yours.
What's that? Yours is different? What does yours say?
You did a question mark after that. I just hit enter.
Yes. So I did question mark to show everybody what everything is. So the first one is either V or A for value or alphabetical order. The second is fraction type, which is either W for mass fraction or X for mole fraction. The third one is either C or N. C stands for composition. N stands for composition and constitution. Constitution means how much are on each one of the sublattice sites. So, if we're talking about BCC and there are 2 atoms per unit cell, and we're looking at a BCC phase that has been described in terms of 2 different sublattices for BCC or B2, it will tell us how much of each element is on each one of those sublattices. So for now, because we're only dealing with BCC, no big deal. When we start talking about BCC B2 ordering or FCC L12 ordering, we will want to know, are those constitutions of the different sublattices the same? Because if they're the same, that means it's a disordered phase, that means it's FCC. If they're different, that means they're ordered, that means they're B2 or L12 gamma prime. So that's where that third one comes in. And the last one is, which phases do you want to show? Do you want to show only the stable phases or all non-suspended phases? I typically don't change that. I typically just only the stable phases. There are times where you may want to show not all non-suspended phases because you may want to know what is the equilibrium composition of this phase that is unstable. Sometimes what we'll do is we will set a phase not suspended but dormant, which means that it's going to do all the calculations for it, but it's not going to consider it in equilibrium. And we can do that to calculate a driving force for precipitation. So say we have FCC and BCC and cementite, and we want to calculate the driving force for the precipitation of BCC from the FCC. Well, if we just calculate equilibrium, we're going to calculate an equilibrium with FCC plus BCC. But if we make the BCC phase dormant, it'll calculate the equilibrium without BCC, but it will give you the precipitate composition and the driving force for precipitation of that composition. So that's that line over on the other side of the curve that we talked about in phase transformation, right? You missed it. You'll get it next year. But get that. So anyway, that's what those options are. Look at the options. It says at a temperature of 1177.75 Kelvin or 904.60 degrees Celsius, a pressure of 1 times 10 to the 5. We have a weight fraction or a mass fraction of 1.234 times 10 to the minus 1. In equilibrium, we have 0.638 moles of FCC and 0.362 moles of graphite. The next thing we want to do to actually calculate the phase diagram is to map out on that grid that we set up when we set our 2-axis variables. So now we've got that grid. We want to map that. So we type map.
Oh my.
Spinning through. It doesn't gobble. It doesn't gobble in the console mode like it does in graphical. Goes through. When it's done, we want to go to our plotting module, which is post or PO. It sets automatic diagram axes. So let's see what that looks like. PL for plot. Well, it plotted mass fraction. That's good because we did our calculation in mass fraction. It plots it all the way out to 1%. And over here, because we did our calculation in Kelvin, it plots Kelvin. So we can set diagram axis Y, TC. Now we change that to temperature, and we could do the scaling status the same way. So we could set scaling status X, no, 0 to 0.1. Set scaling status Y, no, say 500 to 1600. Set diagram axis X, W, B, C. Let me know when you're ready.
The XX. So I tried to do the SSS and then Y 500, 1600 all on the same line, and then
Yep, because you forgot the N. Because if you set scaling status, the next question is axis, Y, automatic scaling. Need to put N down, otherwise it'll get confused.
and 500,
Yep.
1600.
That's why I was going too fast and I did that.
Ah, you
All-
hit enter. Okay.
So yeah, and then for the next one, I actually
A, X, W, P, C.
we will get ThermoCalc on your computer so that you can play around with this. And I will email you and Mary and Isaac, but Isaac's got it for his computer. I will email you and Mary the username and password for the ThermoCalc computer downstairs.
Add me to that list.
What's that, Isaac?
I only have the demo version.
You only have the demo version?
Yeah, because it's
Okay.
product computer.
Okay. Yeah, we'll fix that. The demo version is not going to work for you. And if Mary and Ethan end up wanting or needing to do some calculations for your poster, then we will get you guys set up on your computer. But as Kevin said, the official status is you can put it on a university-owned computer, but not on anything else. But for Serena, who's using her own laptop, and Isaac, who's going to be doing a lot of the ThermoCalc, you know, that's Isaac's primary research. I'm going to have him put it on
Okay.
And if you guys end up needing it, great, we'll do it. If you don't, we'll let you guys use the ThermoCalc computer downstairs and log in remotely. I know you can do it on campus, and I'm going to try to figure out how to do it from off campus as well.
Okay.
And you've got a university-owned computer, so no big deal. So the only one we're really breaking the law with is Serena and Isaac. But Isaac, we'll get that. It's actually on the group drive, which we can put together, but we'll get it for you.
Yeah, cool.
Okay. So the last thing I want to show is we plotted the iron carbon phase diagram again. Looks just like the binary diagram easy. The problem is, still got this dang graphite phase in here. We don't care about graphite unless we're talking about stainless steel, or not stainless steel, unless we're talking about cast iron when we're way out here to 5 or 6% carbon. Most of the time when we're talking about steel, we want to talk about cementite. So let's go back. What we can do is under poly, we can change status. Change status.
Where is that?
What's
Hold
that?
on, change.
It's the fifth option down. Question
Okay.
mark on the left-hand side.
So
I use CH-ST. And it asks for phase species components. In this case, let's change the status of a phase. And let's type in graphite. Enter. What do we want to change it? Right now it's entered, meaning it's being considered. If you press question mark, it gives you a whole bunch of gobbledygook, which why? But if you go up to the top here, you can see for phases, a phase can either be entered, suspended, dormant, or fixed. Well, let's suspend it so that it doesn't even think about graphite.
Doesn't it? I thought that just got rid of your lines.
That is suspend phase in plot under post.
Uh-huh.
If we're in poly 3 and we suspend the phase, we're suspending it from the calculation itself. So under post, it's suspend phase and plot, and it just basically deletes all the lines that has anything to do with that phase. If we're in poly 3, which is the actual calculation module, and we suspend that phase, it's going to ignore that phase when it does the calculations, and it's going to find the equilibrium without considering graphite, which will be BCC plus 7. It'll be 710. So let's list our conditions again. Hasn't changed our conditions, so now we need to compute equilibrium again. Let's list our equilibrium. File to screen, options. Oh, where the heck? Why are we way out there? I'm at FCC. What the okay, I think we're out too far. Set condition WC equals 0.01, no, 0.001. Because we're way out at 12, we're way out at 12% carbon, so it's calculating cementite plus whatever the next lowest energy carbon phase is. So let's go on the other side of cementite. See what I did there?
Mm-hmm. List equilibrium. Yes. I got rid of the diamond.
It did.
Why'd you say dang it?
Oh, because it didn't show what I wanted to do. Set condition. I'm going to set the temperature down closer to say 500 degrees C. Because now you'll see that instead of, why is it doing diamond? All right. We're going to suspend diamond too. There we go. Suspend the diamond phase as well. Because apparently, the iron diamond phase diagram is more stable than the iron cementite phase diagram. So just suspend that second phase too. And then if you're in the proper phase field, you should get BCC plus cementite. When you map it, now we have the iron carbon phase diagram. So let's plot that out too. There, now we don't have to worry about all those other carbide phases that really aren't there, or we really don't care about because they're on the other side of cementite. Look at that, iron carbon phase diagram, iron cementite phase diagram. So, your homework, choose to accept it.
I don't.
Okay, that's fine.
What is it?
Iron aluminum phase diagram.
No. I would not. This is a voluntary class except for PhD students. But PhD students don't have to pay attention as long as they learn it on their own. So you don't have to do any homework. You don't have to come to this, I guess, if you're going to learn it all on your own. But I want to give you guys a hand on doing that. So if you go under help, the example files here will actually open up these different macro files that will run examples. I've never found the macro files under example files too terribly helpful. What I like is if you go under help manuals folder and it pops up this folder under manuals, you go to all ThermoCalc documentation, you'll see a PDF of ThermoCalc console mode example macros. Up here under help, the fourth thing down under help.
I'm still looking.
And so it'll open up an Explorer. If you go under all ThermoCalc documentation, you'll see this PDF that's the ThermoCalc console mode example macros. When you open that up, this is really the Bible of ThermoCalc. You can learn everything you want from this. Well, I won't say everything.
667 pages of
Yeah, so let's try to figure out where the heck everything is. Yes, it is very, very long.
That's literally telling you what it
But
every single input.
this has, and you can go down and you can look at the table of contents, and it's very, very small text, so you have to zoom, so I'll have to zoom back in. And it has 30-some example macros. These are the actual macro files that you can actually go open up under example files. And it'll run it for you, but this has all of the text. So this TC example 1, calculation of the FEC binary phase diagram. It has basically the same macro files we just created. You can go in there and it has every step. And it has some annotations in it. So if we go down here, sys, this is a macro file open, set echo, don't ask me what set echo is, it's something else. Whoop, whoop, oh, schnit. So we'll go here. So anytime you see at, these are comments. See if I can blow this up a little bit. Whoop, too much. So all this stuff under here, these are the comments from the users. Calculation of the discrete phase diagram. This example calculates the binary FE3 phase. So it tries to tell you exactly what it's doing on all of this stuff. And so you can go through and figure out how to do everything. And there are tons of examples in here. And I actually still use these to figure out how to do things here and there that I want to learn how, that I don't remember how to use. So you could take, you know, if you want to plot thermodynamic functions, that's going to be important if we want to do phase transformations, right? We want to be able to plot the thermodynamic functions. I don't know how, or well, I'm sure I could figure out how to calculate free energy differences between between two thermodynamic functions. But that would probably be in here too. You could at the very least, you could say, give me the value of this function at this composition and temperature, give me the value of this function at this composition and temperature, and subtract the two. But you could plot thermodynamic functions. TC example 3, it'll teach you how to plot an isothermal section of a ternary phase diagram. I still use it. I strongly suggest that you start out by doing some of them. We just did the iron-carbon phase diagram, so you can look through that if you have questions about what we did today, which you probably do because I talk really fast, and you know, you can't gather everything at once anyway. So that's there. This recording is also there, so you can go back and listen to me yap for going on 2.5 hours now about iron-carbon phase diagram, calculating a phase diagram with a miscibility gap, iron chromium, calculating a vertical section of a ternary phase diagram. So there's a whole bunch of stuff in here. I've never done most of them, like calculating a property diagram for high-speed steel. I've never done it. I don't know what property they're calculating for, but you can probably do it. Calculated dew point with the poly3. I've never calculated dew point with ThermoCalc, but you can learn if you want. This is, once I was given a course much like what we did today, the way I learned was plugging away at it. Mm-hmm. And so next week we'll play around and we'll either try to calculate a more complex phase diagram. We might go plot some free energy functions, and we'll answer any questions you might have that you've come across over the next week. And if there's something specific you want to do, we can do that. I was calculating phase diagrams as a function of nitrogen content because I was thinking about adding nitrogen to 316 and Inconel. So I think next week we'll do a multi-component phase diagram. I'll try to keep it simple, but it's probably not going to be a ternary because I want more than a few elements. So we'll probably do an example having to do with 316 and nitrogen next week, or Inconel 625 and nitrogen plus, or whatever we want to do. We've got 2 hours blocked off. I don't expect to use 2 hours every week, but we'll use this time. I'll talk about what I want to talk about unless somebody else has something else they want to learn, and then we'll do that. That sound like a decent way forward? Thank you all for listening to me talk for 2 hours and 13 minutes.
Looks like I have been listening to you talk way longer than that.
You have listened to me talk for 50 minutes plus
2 hours.
2+ hours plus another 2+ hours. My good Lord, how can you even stand to be in the same room with me at this point in the day?
You pay us to.
I suppose I do. Good answer.
Good answer.
All right, I'm going to stop sharing my screen. Isaac, do you have any questions?
No, I guess not. Just from looking at what I need to like get the actual Thermo-Calc, it looks like I
Yes.
need like a file, or like you need to email them.
You do, and I'm going to show you that right now. Okay, so I'm sharing my screen again, right?
Yeah.
So you should have access to, under your Google Drive, you should have access to last group.
Yeah, I do.
And under last group, there's ThermoCalc. And under ThermoCalc, there's a couple of different install files. This is the 2019 version. This is the latest version, the 2021 version. So you can just download this ThermoCalc file to your computer.
I have like installed it.
What's that?
I have
You have that
installed.
file?
Yeah, I have installed the program. It just asks for a like a license file in the
License
wherever
path,
it's installed.
right here. mabe59.mabe.utk.edu. It's
I don't
under
get the
here.
option to, like it asks whenever I open it up, it asks for, like there's I guess a text file or some sort of file in the installation folder that's missing.
Yeah, you need to install it as a network. Please don't screw this. Please don't screw my version up. Please don't screw my version up.
You can just explain me or tell me what.
I can't remember for sure it is, but there are multiple options for installation types. You want to install it as a network installation, and it will ask you for the location of the license file. It'll ask you for the server that the license file is on.
Okay. Okay, that makes more sense.
And so by default, the installation is like a single computer or something like that.
Yeah.
And so you probably tried that and it was looking for a specific license file that's not in your folder. But if you click on network license, it'll ask you for the license path. And that's where you plug in the mabe59.utk.mabe.utk.edu.
Okay. I'll get that done then.
Try that. If that doesn't work, we'll get you figured out. We'll
Sweet.
figure it out some other way.
Thank you.
You're very welcome. Have a great weekend, Isaac. If you need anything, shoot me an email.
Will do. Thank you.
All right. Thank you. Bye.